And we'll go ahead and scroll down a bit. So I've got this broken up into a couple of sections just so we can have space to write. But this problem is usually seen on the calculator portion. And so there are certain things that we see a lot. The first two parts we really don't need a calculator for. And it's usually not until we get to the modeling function, which is part C and D, where we would need the calculator. And I'll explain why we don't need the calculator when I get to those problems. So Joanna jogs along a straight path. For 0 less than t less than 40, Joanna's velocity is given by a differentiable function v given by this table. And part A says use the data in the table to estimate the value of v prime of 16. And you'll notice that there is no 16 on our table. But it does lie smack between 12 and 20. And I know that I can estimate v prime of 16 by looking at the slope between 12 and 20. So v of 20 minus v of 12 over 20 over 20 minus 12. Keep in mind this is an approximation. This is not the actual value. So when I approximate this, this is going to give me 240 minus 200 over 20 minus 12. Now, I'll tell you right now, number one, I'm lazy. But number two, you're not going to get any extra points if you simplify this. However, if you simplify it wrong, I guarantee you're going to lose points on this. What is very important here is that we are trying to estimate a velocity, and so we do need to make sure that we have our units, which is going to be meters per minute. And this is another one of those problems where you're going to need to put your units on all of your answers. So for part A, we're looking at this for our average rate of change, which is an approximation of our instantaneous rate of change. On part B, it says, using correct units, explain the meaning of this definite integral. Now, the thing that's important is the fact that we have absolute values here. And so this is not velocity, this is actually speed. And if I'm doing the integral of this, I'm integrating speed, which actually tells me the total distance traveled, because I'm going to be moving forward a certain amount, and then I'm going to be moving backwards an equivalent amount. So the integral from 0 to 40 of the absolute value of v dt represents the total distance traveled in meters from t equals 0 to t equals 40 seconds. So that's what it represents, and what I've accidentally cut off here is that it's asking for us to approximate this using a right Riemann sum. So because I'm doing a right Riemann sum, I'm going to be looking at the right endpoints, so the rightmost data values for the rectangles that we're looking at here. So I can say that the integral from 0 to 40 of the absolute value of v dt is approximately equal to, this first rectangle goes from 0 to 12, so this would be 12 minus 0, times the height of the rectangle, and we're using the right endpoint, which is 200. Plus my next rectangle, which goes from 12 to 20, so this is going to be 20 minus 12, and the height of this rectangle is going to be 240. Plus, this next rectangle goes from 20 to 24, so this is going to be 24 minus 20. And the height of this rectangle is not 220, it's 220. It's not negative, it's positive because of this absolute value. And then I've got my last rectangle, which goes from 24 to 40, so this is 40 minus 24, times the height of this rectangle, which is 150. And I'm not going to try and do anything more with this. This is perfectly well and good. This is simplified as far as I need to simplify it for the AP exam. I'm not going to waste time trying to make this more simplified. So that's part A and part B. So now let's take a look at part C. So for part C and part D, they give us a modeling function, and that's really what's different here. They give us a modeling function, and they tell us that Bob is riding his bicycle along the same path. It says for 0 less than t less than 10, Bob's velocity is modeled by this formula, where t is measured in minutes and b of t is measured in meters per minute. Find the acceleration. Now, normally this function's very complicated and we have to use a graphing calculator. That's why this problem usually shows up on 1 or 2. But because we're dealing with something that's just a polynomial, it's going to be very easy for us to take derivatives and antiderivatives because it's polynomial. So in this problem, remember that this is supposed to be a velocity function and they're asking us for acceleration, which means our acceleration is going to be equal to whatever b prime is. And so I need to take the derivative of this at 5. So I'm going to have t cubed's derivative is 3t squared, so that's going to be 3 times 5 squared. And, minus. This is going to be the derivative of 6t squared, which is going to be 12t, so 12 times 5. And 300 is a constant, so its derivative is 0. Now again, remember this is acceleration, so I need to talk about the proper units. Velocity was in terms of meters per minute, so the acceleration is going to be meters per minute squared. So for part C, this is as good as we need to get this answer here. And then we've got part D, which says, based on the model from part C, find Bob's average velocity during the interval from 0 to 10. Well, remember that this is a velocity function, so if I want to find the average velocity, then I'm going to have to use the 1 over b minus a times the integral from a to b of our function. This is t cubed minus 6t squared plus 300. So this is our average the average value of a function formula. It's really our fundamental theorem of calculus, because this is really antiderivative at 10 minus the antiderivative at 0 over 10 minus 0. That's really what we're calculating here. So the antiderivative of this is going to be t to the 4th over 4 minus, this is going to be 6t cubed over 3 plus 300t. And no, I'm not going to simplify this. The only thing I'm going to do is I'm going to put this 1/10 out in front, and I'm going to evaluate it from t equals 0 to t equals 10, and I'm going to substitute. So this is going to be, let me make sure I've got my equality here, it's going to be 1/10 of the expression, 10 to the 4th over 4, minus 6 times 10 cubed over 3, plus 300 times 10. And I would put minus and a whole bunch of other stuff, but substituting 0 into this polynomial gives me 0. So my average velocity is going to be this expression, and this is going to be in terms of meters per minute. So this is what we're looking at for part D. So now let's talk a little bit about points. Typically what we've done on part A, because that's dealing with the average velocity, the average rate of change to represent an approximation of the instantaneous rate of change, that's usually just a 1-point calculation. On B, we're looking for our explanation. So our explanation of that, including the correct units, is going to be 1 point, and our Riemann sum is going to be 1 point, so probably 2 points there. Then we have our acceleration, so recognizing the acceleration is the derivative and then actually substituting in the derivative points, that's going to be another couple of points. And then using the average value of a function, you're going to be probably a point for this and a point for the constant and limits and another point for this. And again, with the idea that because we're dealing with units, that 1 point is going to be dealing